ut hx ux equals 0. Let's forget about the initial condition for now. And here u goes from RD 0 infinity into R. It can be used to model a growth. So here, think of u as a height function, say separated in different phases. That's the way to think about it. So, okay, so you have some height, maybe it's the boundary of a crystal or something, it may have corner, and it's changing with time. So this is x, u. In fact, you should think of here x, t, and u are microscopic coordinates. And to go to the corresponding macroscopic coordinates, you use some big number or small number to represent the ratio of these two scales and rescale things. To go to the macro coordinates, choose, say, n large, and consider un xt equals nu x divided by n t divided by n. So again, if now t and x and un are macro, so if you give me a macro t, I divide it by n to go to the correspond. No, the other way around. No, the other way around. Yeah. If n is large, I have the habit of using epsilon. That's why. But purposely, I'm using n here because I want to kind of relate to some quotient dynamical systems. So if you give me macro x and t, you kind of dilate it by a large factor. Then u is micro. You divide it by n to make it macro. Okay? And now un solves this equation. That should be now solved for a suitable initial condition, and you should think of G as a choice for the macroscopic initial data. So you want to solve this. Now, writing let me call this one, TTH for the semigroup associated with 1, that is, if TH U0 at x is UXT, okay, that's what I mean by this notation. You start with some initial condition. Then TTH represents the solution at later time, at a later time. So if it's UXT, then U solves 1 subject to the initial condition Ux0 equals U0x. So that's what I mean. So if I write it this way, if I use the semigroup, then in fact, this UN is a solution to Hamilton-Jacobi for which the Hamiltonian has a fast coordinate. So if I use this notation, what we really have is that if you look at the corresponding semigroup for this guy, which you obtain from H by some rescaling, so that rescaling is denoted by gamma n, then this TT is nothing other than playing the following game. I'm going to explain everything here. Where gamma n xp is n times xp. So the goal of this gamma n is that sending the macro coordinate, macro position to the micro position, but not doing anything to the momentum variable. And the job of this gamma n is send a macro profile for the height function to the corresponding micro profile of the height function. And gamma n of g at x is basically, so basically, if you give me this initial condition, I can rescale things and turn it to this original problem, but now g has to be switched to a profile which is micro. So basically, you give me this g, x now is micro, and so g is macro, but this is supposed to be the corresponding microscopic profile. So this, this micro coordinate should be divided by n. You apply g on it, but this height is macro. You want to make it micro, you multiply by n. So this gamma n is macro g is sent to micro gamma n g. So one way to think about it is that you give me a macroscopic profile, turn it to the microscopic profile, evolve it for the microscopic time nt, and then turn it back to the macroscopic profile. Very simple intuitively. In particular, if I write a tk for th1, so when time is 1, I don't bother to write time. If this is a short notation for this, then what happens is that you're really interested in an operator. So I'm going to put t equals 1. In fact, once you understand this for t equals 1, then you have enough information to kind of figure out what's going on in general. So basically, what you have is this. First, you turn something to micro, and then you look at this operator th. You iterate it n times, because this enjoys semi-group property. So this is really the time 1 map raised to power n. And then you turn it to corresponding macro profile. So that's the way to think about it. So the art of homogenization is to figure out under what conditions, if any, this has a limit. So we are interested in limit n goes to infinity of th gamma n as n goes to infinity. So under what conditions? In general, of course, this is helpless. There's no reason by rescaling h you have any limit for this operator. However, if, for example, h happened to be periodic, you have a very fast oscillation on Hamiltonian. Hamiltonian is very oscillatory. Maybe something is averaged out in some sense. And that's exactly what we want to understand. Under what circumstances this limit exists? So that's the question. For example, if hxp, so the Hamiltonian, so think of this as a position of momentum, is 1 periodic in x, then the limit exists. So this is a very classical, by now, very classical theorem of Lyon's, Papanikolaou, and Fraydoun. Maybe 1984, I forgot the exact year, or something. I can ask, of course, but Raghu may not remember. Is this year correct? Kind of. Yes. It's never published. Right? So you give me a function. I want to know whether for a reasonable function, whether for that function exists, point-wise, for every, yes. So you put a function here for given g, whether this limit exists. Okay. Now, let me mention that if the limit, this guy is periodic, but if the limit exists, in some sense, the only possibility for this, because of the structure of this, You should think of this as some operation. You give me an H, then the semigroup TH turned to a sequence of semigroups. Now somehow, if this guy has a limit, basically this operation sending TH to TH gamma n should not change. In other words, it turns out the limit would be the one for which is the fixed point of this operation. And in fact, the limit, that's the way to think about it, would be T of some H bar. And the only possibility for H bar, because of this periodicity and all that, and because of this operation somehow has to go to the fixed point, is that an H bar that is independent of position with H bar independent of position. Note that if you do T H bar gamma n, this is the same as T of H bar. So somehow it's a fixed point of this operation. Okay, so now we may go beyond the periodic scenario in the following way. Namely, so let's have the following setting. Namely, write H for the space of all Hamiltonian functions under certain regularity. Space of all Hamiltonian functions. Okay, so take the space of all possible Hamiltonian functions. So I want to go beyond periodic functions. So I'm talking about all Hamiltonian functions, not necessarily periodic. And define, there is a natural translation, notion of translation on that space. Namely, you translate the Hamiltonian function in space variable. Define tau A of H of x and p equals hx plus a p. Pick a probability measure on p. So pick a probability measure on h. On h. So now I'm wondering, so in the previous case, I had a periodic function, and then since it was oscillatory, I had a chance to have some averaging phenomenon going on for me. Now, standard way of going beyond periodic is that you choose a probability measure on the space of all Hamiltonian. You want to say, with respect to that probability measure, if it's translation invariant, if you pick a random Hamiltonian, then something like this is true with probability 1, something like that. So that's the standard way of going beyond periodic functions. So a measure P on H that is tau A invariant and ergodic. And ergodic. And ergodic means somehow you want to make it kind of irreducible. If it's not ergodic, then you would have a theorem for each ergodic component. For some H bar that is constant on each ergodic component, you are hoping that ergodic theorem would allow you to have some H bar that is not random on each ergodic component. So, and we may hope that for such P, we can show that T H gamma n, the limit of this, exists with probability 1. So meaning for almost all traces of H with respect to this particular probability measure, then you have this limit with probability 1 with respect to, and this H bar is, independent of P of your choice of H is deterministic. If this happens, we have homogenization. We have a homogenization. We write, so maybe I use this notation. You give me a probability, such probability measure. For such probability measure, I can come up with a deterministic Hamiltonian that is H bar. So this is as if I'm defining this highly non-trivial operator on the space of translation invariant probability measure that would yield a deterministic Hamiltonian. So maybe I use this notation. And note that, so this is just a generalization of the previous case, periodic case. Namely, note that if P happen to be concentrated on suppose I give you just one Hamiltonian, H super 0, take all the translets of that Hamiltonian, and my probability measure P just concentrated on this set only, just various translets of one Hamiltonian. If that Hamiltonian happened to be periodic, when you translate it, this is really, topologically speaking, is the same as a torus, because after one period, you go back to where you started from. So therefore, this probability measure that you want to put on this would be a probability measure on the torus. And since the probability measure is supposed to be a translation invariant, that would be a translation invariant probability measure on the torus, which is just Lebesgue measure. And if you do homogenization for this particular case, you're back to the previous case. Because the whole thing is just various translets of the same Hamiltonian function. With H0 for some H0 that is periodic, is one periodic, we are back to the previous case. So kind of probability somehow is artificial here, because if you prove something for a translet of H0, then it's true also for H0 by simple manipulation. Because the only thing that is there is just various translets of H0. Back to the previous case. In fact, if you give me one translation, one H0 and translate it, but it's not periodic, however, the space of all translations is pre-compact. Namely, if you take the closure of it, you get a compact set, then such H0 is called almost periodic. So that would allow me to have an H0 which is almost periodic, then I translate it, then I prove something that is true for not necessarily the translets of A, but the various limits you get of those translations. Then this theorem would say that now for all choices of the limiting points of various translates, you have the theorem for. So that's when you really, the probability plays a role. And if, so the other classical case is that if tau 0, H0, A in RD, the closure of this is compact, then such H0 is called almost periodic. Then H0 by definition is almost periodic. That's the definition of being almost periodic. And it turns out that in fact, because this is a translation, you can combine two translations, get another translation. There's a group structure on this. Then it turns out that this becomes a Lie group. And this probability measure you want to put there is nothing but the Haar measure on that group. And so kind of, then you don't need that much of probability, but you basically dealing with a group. OK, so this is the kind of thing you want to prove. You want to prove homogenization either in periodic case or random case. OK, so keep this story in mind. Now I want to kind of contrast it with another story that you can develop parallel to this. And that has to do with the fact that there is a very intimate relationship between Hamiltonian ODEs and Hamilton-Jacobi PDEs. And I want to kind of use this to motivate a question that you can formulate for just Hamiltonian ODEs. And you want to do homogenization on that. So I erase the title. That's what I mean by two homogenizations. And the natural question would be whether these two homogenizations are exactly the same. And the answer is not always. So OK, so right. So here, when I pass to the limit, I get a semi-group associated with some Hamiltonian. So initial data, I assume, is a kind of reasonable initial, let's say, Lipschitz function. For example, Lipschitz function or something. I don't know if I understood your question. Okay, so I start with a macroscopic function. Macroscopic function, yes, it's always macroscopic. So, okay, so the goal of homogenization is to go from microscopic coordinates to macroscopic coordinates. So what it really means that microscopically, I have this Hamilton-Jacobi PDE with spatial dependence on the Hamiltonian. But then when you go to macroscopic coordinates, you have a reduced and simpler description in which the Hamiltonian, you still have a Hamilton-Jacobi PDE, but the Hamiltonian function now is independent of position variable. And that simplifies the PDE drastically. However, the relationship between H bar and H is so complicated that it's not clear that there is really a simple, because you don't have a nice formula for H bar. But that is the kind of, I mean, that's the philosophy behind. Oh, yeah, no, yeah. I mean, you see, I didn't continue that direction. I wanted to add some external force that would turn into this problem. But I didn't go that far. Yes, no, that's different now. That's right. All right. So, but there's an intimate relationship between Hamilton-Jacobi PDE and Hamiltonian ODE. Let me quickly mention a couple interesting things that happened there that would allow me to come up with a kind of the correct formulation for homogenization for Hamiltonian ODEs. So to, as a warm-up, let's now to say more on this, let us explore the connection between the Hamilton-Jacobi PDE1, I erased it, and the Hamiltonian ODE. The Hamiltonian ODE is this. Okay, and write phi t xp or phi t z. So sometimes I write z for the pair x and p. So this is kind of the coordinates in the phase space. Okay, so you have position and momentum. And this is the flow of this. So this means a solution to this problem for which z is the initial condition is write this for the flow. Call this 2 of 2. Okay, the notation is clear. So I'm kind of abusing the notation here. I write in xp for everything, but now here xp is the initial condition. Maybe I feel bad. So now this represents, now this is xtpt. This is xtpt. Okay, so what's the relationship between these two? So again, I'm going to rewrite one for you. So remember, we want to solve this. In fact, I think Jacobi, well, Hamilton-Jacobi. Did Hamilton-Jacobi define Hamilton-Jacobi? I doubt it. I guess Hamilton defined Hamiltonian ODE. Jacobi figured out that if things are completely integrable, then there's something called, physicists call it generating function. The generating function satisfies the PDE. That PDE is Hamilton-Jacobi. Probably that's why it's called Hamilton-Jacobi. You know, Jacobi derived that PDE for the so-called generating function of the change of coordinates you need for Hamiltonian ODE to turn it to a completely integrable situation. Okay, so we want to kind of solve this. And now, so how you can relate the two? Indeed, so what's happening is that the method of characteristic, by the method of characteristics, what's happening is to solve this, you differentiate the initial data and regard that as an initial condition for the momentum. So you look at the set x gradient u0 x. You vary x. So that's the graph of the derivative of the initial data. This derivative of u0 is the one that in the previous lecture I called it rho, which solves a scalar conservation law. So if you look at this, so you just this is u0, derivative of u0 versus x, suitable function, and then you evolve these such initial conditions for different positions and different momentum with this relationship between position and momentum according to the ODE. Okay, so you kind of apply phi t on this, then you get a suitable curve. Now, for short times, in principle, when you apply phi t on a graph of a function, the outcome may not stay a graph of a function. But if it does stay as a graph of a function, it is indeed the graph of a function of the solution at later times. So this, in fact, is true for short times or at least locally. This is the same as ux xt x in Rd. So in other words, if the relationship between momentum and position is given by this, namely momentum is the derivative of some scalar value function with respect to x initially, then at later time you have a similar relationship, but now you have to use the evolved solution of the PDE to figure out what relationship you have between x and position, momentum and position. Though this may not be, this may not be true in general, because the left-hand side may not stay a graph of a function. So a more realistic picture would be you get a picture like this. Okay? But then what you can do with the solution? In fact, when this happens, this is when you fail to have classical solutions. You see, if this doesn't happen, you have this, then you have a classical solution to the PDE. But when something like this happens, this is when you have to come up with a different recipe for constructed solution. Method of characteristics fail to give you the solution. And what happens is that basically you want to perhaps trim this guy a little bit to turn it to a graph of a function, and then that would be the graph of function of the solution of the PDE. But if you trim it, then you have to give up the notion of classical solutions, because as you see, you would have a jump discontinuity. Jump discontinuity for the derivative of u is equivalent for not having a C1 solution to the original PDE. So, but in general, we need to trim it. I don't know, trimming is the right word. In general, maybe is not clear, because I have to figure out how to trim it. It's not clear that in a kind of satisfactory way I can come up with some universal way of trimming this guy that will give me a reasonable generalized notion of solution. So in general, maybe we need to trim the left-hand side in order to find the solution, to come up with a reasonable notion of solution. So think of it as some kind of geometric way of looking at this problem. But it turns out that it's not clear such trimming is always possible. And is this possible? So this is a kind of rather naive geometric way of thinking about the problem. Can I really come up with a very precise mechanism for how to trim this so I have some kind of notion of generalized solution? That is not known yet. However, analytically speaking, an alternative way is to add a Laplacian a small viscosity to the solution, pass through the limit to see what happens. Then the question is whether, when you do that, you do get a trimming. The answer is not always. So however, or alternatively, you may consider u epsilon t hx u epsilon x equals epsilon Laplacian u epsilon x0 equals u0 x, and send epsilon to 0. Okay? Because now I have a classical solution. Then if I can show that the limit exists, and under some mild condition on h, the limit does exist as epsilon goes to 0, you have a candidate for what the solution should be. And that would be a general solution. Now, and this way, we get the so-called a viscosity solution to 1. Does viscosity enjoy the following property? Is it really a trimmed version of that curve? The answer is not always. And that has to do with the so-called contact discontinuity that might be produced later on in the solution. And that would you insert a piece of solution that has nothing to do with initial data, and then somehow turn this into something that has a piece in it that doesn't come from initial data. So a natural question is whether, if you apply phi t to the initial data, and if you compare it to the solution at later time, and under some mild condition on h, you can guarantee the solution you get using the method of viscosity is differentiable almost everywhere. Some mild condition. If initial condition is Lipschitz and the solution grows, h grows sufficiently fast at infinity with respect to p, then you can guarantee that the solution is almost everywhere differentiable. So to make sense of this, I would say x in Rd and ux is differentiable at xt. So let's look at this. And then you wonder whether this is a subset of this. So that's the question. If that is the case, that means you got the solution at later time by trimming what you get by just applying the flow of the ODE. Okay, answer? Yes, if H is convex in P. Not always if H is not convex in P. Okay. Okay, I'm not discussing all these technical issues, but you see, to have a reasonable solution which has some regularity, you have to assume H grows sufficiently fast at infinity with respect to P. But I'm just this kind of heuristic, and I'm not dealing with all the. No, it is crucial to have some regularity of solution. I mean, for the existence of viscosity solution, all you need is coercive, meaning H, something like that. And then if you want almost everywhere differentiable, you need to assume more, not only coercive. You want to assume that it grows like polynomially at infinity or something. But I'm not bothering with those things. I just want to give you a big picture. Modulo technical conditions, whatever I say, true. Okay, so far so good? Okay, so that's the story with Hamiltonian ODE. So still, there's some connection. It turns out that people in symplectic geometry came up with a version of the solution. They call it geometric solution, for which this condition is true. The solution is almost everywhere differentiable. At every differentiability point, satisfies the PDE, and is not viscosity solution. However, the solution suffers from a big drawback, doesn't have semigroup property. because it has other properties that, if you put other properties and semi-group property, then viscosity solution is the only choice if you have the monotonicity of the operator or something. And that's why their solution is not satisfactory. But I get back to that later. Okay, so we heard two stories, Hamilton-Jacobi, homogenization, Hamiltonian ODE. Now, based on this, on the intimate connection between Hamilton-Jacobi and Hamiltonian ODE, we may wonder whether you can formulate a homogenization for Hamiltonian ODE directly. And the hope is that this homogenization would coincide with the other homogenization, at least when H is convex. It turns out the homogenization I'm going to formulate does coincide with this homogenization only when H is convex. If it's not convex, it gives you an alternative homogenization problem. So based on the intimate connection, we may wonder whether a homogenization question can be formulated. A question can be formulated for Hamiltonian ODEs. So what I mean is that either the Hamiltonian ODE is periodic in position variable, that would turn the problem on a torus, or is random for the Hamiltonian ODE. So that's the question. And in fact, I have a candidate for, more or less, I have a candidate. Eventually, I'm going to come up with a reasonable formulation, and then I formulate some conjectures and state the theorem. So since there is no next lecture, I don't have to adjust things so that I reach a very exciting point, right? So, OK. OK, so far so good? OK, so now, here's the formulation. Let's make the following observation. So recall that previously we looked at THO gamma n. So this is when you rescale the position, but not the momentum. You make a change of you do a rescaling for the Hamiltonian. So you make the Hamiltonian very oscillatory. That's what you do, only in position variable, not momentum. And that was okay. Now observe. Now observe that if you look at the flow of this Hamiltonian, let's examine the flow of this Hamiltonian. What do you get? What happens is that basically what gamma n does, you give me a macro location, it turns it to a micro location and apply the semigroup here. It turns out that is the same as you give me, it's the same as you give me a position and momentum, turn the position to a micro, a corresponding micro location, apply the Hamiltonian for the corresponding micro time, and then turn back the position to its macro location. So that's exactly what you get, which has the same flavor as this. Previously, remember, you can just put T here as well if you want to. The same thing is true. OK, so that's exactly what happens. So this is really long-time behavior. After you're switching from macro coordinate to micro coordinate, you wait for a long time. It has to do with long-time behavior of the solution to the ODE. And then you go back to the macro location. Because if you're far away, You wait for a long time, you're really far away. Go back to have something reasonable that has a chance to have a limit. Or when t equals 1, what you really get, and yeah, and if we write phi h for phi h1, the so-called time 1 map of Hamiltonian ODE. So you have a Hamiltonian ODE with a flow, and just evaluate set t equals 1. This is a time 1 map, which gives me a discrete dynamical system. So you have a Hamiltonian ODE. You kind of look at the time 1 map. Then the time 1 map of this rescale Hamiltonian is really gamma n, the time 1 map of the original Hamiltonian, which is not rescaled, raised to power n. You apply it n times. So you have a discrete dynamical system. And then you turn it back to the macroscopic coordinates. That's what you get. Now, question is, does the limit of phi h gamma n as n goes to infinity exist? So that's the question that you may regard it as the analog of homogenization problem for Hamiltonian ODEs. Is this true? And if this is true, then we expect phi h gamma n in some sense. I'm not telling you in what sense. That's actually would be the main question today. Is there a kind of reasonable topology for which you can ask this question? And all the standard topologies would not work. That's the point. Okay, so is this exists? And if it exists, you call that H bar. We expect something like this to be true for some H bar, such that, in fact, if you play this game for H bar, you get nothing. This is a fixed point of the operation, such that if you look at gamma n inverse, phi h bar n gamma n, then you're not getting anything new, and basically because h bar doesn't depend on position. Because, in fact, this is more or less equivalent. You really go to the fixed point of this operation. Think of this as an operation you do on the time 1 map of a Hamiltonian ODE. So because h bar xp is independent of position, and phi h bar in this case is really x plus gradient h bar p p. The flow has a very simple form, because this is the situation, the so-called completely integrable situation, when h bar is independent of position, and all you do, p doesn't change, and the position just go straight line, along a straight line with that slope. Okay? Now, the main question is in what sense the convergence, in what sense, if any, it's not clear this has any chance to be true, if any, the convergence happens. In what sense does this convergence happen? In what sense for phi? Well, there are two things involved here. So you give me a Hamiltonian ODE, there is a Hamiltonian function and flow. There are two things. So either I may hope to find a notion of convergence that involves the Hamiltonian function directly, or I have a notion of convergence that involves the flow of the Hamiltonian function only. So there are two spaces that I'm dealing with. On one hand, we have a scalar value function, namely the Hamiltonian functions. On the other hand, I have this diffeomorphism on the phase space. So I either have to put the topology on this one or the other one, and you can go back and forth. Now, the convergence, the pointwise convergence, or LP convergence, or any convergence you can think of, on the sequence seems to be helpless. Because if H is, for example, periodic in a space, then when you rescale it by n, this is so oscillatory, it has no chance to converge. The pointwise convergence for H gamma n is helpless. And for phi H gamma n is not true either. But then actually, it turns out there are two topology exists on the space of Hamiltonian or on the space of the flow associated with Hamiltonians, that in that topology, and these are very important topology when you study Hamiltonian ODEs, they have a chance for which this question might be true. The convergence may happen in those spaces. So, so we already defined H, space of Hamiltonian. Let us also define I don't know what to call it, maybe K, be the space of the corresponding flows, time one map of Hamiltonian functions. This would be the space of phi H1 with H in H. And in order to have a nice topology here, I have to assume some structure here. For example, either I assume H is periodic in a space variable or has certain behavior as X gets large. But let's look at this for now, OK? So this is the kind of, in reality, we may put more restriction on H. But I'm not going to discuss those technical issues for now. Just kind of focus on the big picture. Now, it turns out that so far we know of two metrics on these spaces that may play a role here. And in fact, we have a theorem for homogenization with respect to one of the metrics. So it turns out there are two metrics. Though to show this is a metric, it's easy to define something that claim that's a metric. But to make it work and to be right for our purposes, that's a different issue. So it's highly non-trivial. Even the definition is rather non-trivial. At least one of them, the definition is very hard to give a straight definition for it. But one of them is easy to define, but it's extremely hard to check it is a metric. So there are two metrics on K or H, because they're kind of more or less the same. You can go back and forth. The way I define this, somebody's in here if it comes from there, for which you have a chance to make to have a convergence. For our sequence. So these metrics, these are defined by people, experts in symplectic geometry. One of them is called Hofer metric, the other one Viterbo metric. Were defined by Hofer and Viterbo. And now let me mention that there's a recent paper of Viterbo. It's not published. It's like 90 pages that claims he can prove homogenization with respect to his metric. So theorem. And they kind of in the periodic case, but hopefully it's also true for a random case, but that's an open problem. So Viterbo, phi h or gamma n converges to phi h bar with respect to Viterbo metric with respect to Viterbo metric. And if H is periodic in space, is one periodic in X. Write a hat H equals H bar. So you give me a periodic function in a space variable for a Hamiltonian function, though he has to assume that H is of compact support, is periodic in space and compact support in P. Okay, so maybe I should periodic in X and compact support in P. In fact, this makes a huge difference when it comes to the proof. But nonetheless, still, the paper is 90 pages long. And it's all heavy-duty symplectic geometry, believe it or not. OK, so this is true. And write this for this operation. So you give me an H, and I turn it to H bar. Remember that we did previously for viscosity solution, we defined an operator. So recall that if you look at T gamma H gamma n, this converges to T. Maybe I call that H hat actually, because they are different. This converges to some H bar. And I use the notation of, maybe I use the notation H is H bar. So if you do viscosity solution to Hamilton-Jacobi PDE, that gives you a homogenization for which H, say periodic function, turn to a Hamiltonian that is independent of position. If you use this theory, you get some H hat that is independent of position, and you have homogenization for Hamiltonian ODE. What's the relationship between these two homogenizations? And what Viterbo shows that, moreover, A bar of H equals A of H if H is convex in P. Otherwise, in general, A hat of H is not A of H. OK, so I formulated two homogenization questions. One was for Hamilton-Jacobi PDE. I can do the homogenization. You give me a Hamiltonian function that depends on position. That would turn it to a Hamiltonian function that is independent of position. H is of compact supporting momentum variable, meaning for P. OK, so yes. You see, that's right. That's right. So, OK, good point. He proved it for Hamiltonian, which are not of compact support. But there must be an extension of it that goes beyond it. If that extension exists, yeah, you're right. I'm being a little bit sloppy here. Then that extension has no chance to be equal to the other one in general. Maybe that's a better way of stating it.
There's nothing to do with the
you mean the well? That's right. It's exactly of broken characteristics. That's right. Okay, so you are opening a kind of a box that there are so many questions in that. I tell you what the story is. In this metric, so you define a metric on a space of Hamiltonian ODEs. And that metric, nobody knows what's the completion of that metric. So, okay, so put it differently. This metric is in such a way that you define it, it should make sense even for a Hamiltonian function that is only continuous. And somehow, if you figure out what solution, and there is a chance to make sense of a Hamiltonian ODE for which the Hamiltonian function is only continuous. But what solution means, nobody knows. That has to do with a question of completion. If you figure out what the completion is, then probably the broken characteristic shows up there somehow. Roughly, I think that's what's going on. Yeah, you're right. I mean, it's not clear because you're right. I mean, if you go along the characteristic, when you reach the shock, then you have to travel, along the shock. And then that is not clear what do you mean by solution to the ODE. But somehow it's as if I make sense of the solution of ODE when you have several choices for the initial data, and then the characteristic would tell me you make a choice in between. You go along the characteristics. Like, kind of Filipov type of solution or something like this. So that has to do with the completion, understanding the completion of this metric and make sense of very generalized solution to Hamiltonian ODE. You see, we have some candidate for generalized solution to Hamiltonian PDE, but not for the ODE. That's the same as geometric solution. So in Russian school, they call this something else. They call it, I think, variational solution. In French school, they call it geometric solution. They are the same thing. Yeah, no, this is the same thing. We call it, this is something that I call the geometric solution. I give a definition. That is exactly what I have in mind. That gives an alternative way of solving the Hamilton-Jacobi PDE. What you mentioned is exactly that solution, which is satisfies the PD almost everywhere, but is not the viscosity solution. No, they're the same. Yeah, they're the same. Yeah, I mean, I've been looking at like all the papers in this context. They are. That's right. So, actually, I mentioned his theorem is true for some compact support, but that shouldn't be needed. So this operator should make sense even for H, which is not of compact support. If such an operator can be defined for general H, even those that are not of compact support, then they cannot be true if H is not convex in P. But they should be the same. Convex everywhere. So again, let me repeat it that he put this technical condition, compact support in P. But what I'm saying is that the theorem should be true even for H, which is not of compact support. That would allow me to include convex functions also. If I'm allowed to include those guys, then they should not be the same. In fact, let me mention that the homogenization you get here is a homogenization for that solution you mentioned, the variational solution to the PDE, not this kind of solution. Yes? Okay, so yes, okay. So I defined it in the random case, but if it's periodic, I'm abusing the notation. I use A of H for A of P if P is supported on the translist of one dash. So I'm abusing the notation. I apologize. Any more social? I know it's a little bit confusing, but okay. So now let me say a little bit about the metric. So other properties of this. So right, I mean here because of his theorem, I cannot include the convex functions. But imagine you can extend it, and you can include convex functions also. Then that should be true. So some properties. Of a hat that are not true for A, and these are very essential because A hat ultimately is related to Hamiltonian ODE. So one of them is this. Suppose you look at a hat of h1 plus h2. Then this would be the sum if the Poisson brackets of h1 and h2 is 0. In other words, if the corresponding Hamiltonian ODE, they commute, then you have this additivity property. This is not true for the other homogenization in general. Not true for A, unless both H1 and H2 are convex. So that's one question. So if you have two Hamiltonian, they Poisson commutes, then you have this property. Okay, so let me mention another property which is not true for A, but is true for A hat. A hat, now, suppose you make a change of coordinate of H, that is the so-called symplectic change of coordinates that is very compatible with Hamiltonian structure. In other words, suppose you take a phi that is in here. Take any transformation that comes from some Hamiltonian ODE and compose it with H. That gives you a new Hamiltonian. Then this is the same as H for phi in K. Not true for the other one. For A, unless both H and HO phi are convex in P. So now let me, okay, so going back to the metric. Now I want to say something about the metric. So I want to say something about these metrics and, okay. So let me write D for Hofer metric. And write dV for Viterbo metric. In fact, when you study the Hamiltonian ODEs and examine the behavior of solution under that metric, there is a name for it. It's called Horrid Geometry. There are various things. You really should think of this metric as some kind of putting some, not exactly Riemannian structure, but Finsler structure on the manifold of Hamiltonian ODEs. And then doing any geometry there is known as Horrid Geometry. For example, people figured out what the geodesics are exactly with respect to this metric. And they show that the space of Hamiltonian ODEs locally is flat with respect to Hofer metric. And it turns out that the Viterbo metric is less than always the Hofer metric, and they are not equal in some cases. So doing homogenization with respect to Viterbo metric does not imply the homogenization with respect to Hofer metric, because that's a weaker metric. So it's not clear that you have the convergence with respect to Hofer metric. So the question or a conjecture, I don't know how to put it, well, conjecture is a statement, but let me state that. So I'm going for the middle ground. So I state a conjecture, but in the form of a question. It's true conjecture. dH of phi HO gamma n, phi H hat, okay. And let me tell you what it really means. If this conjecture is true, it gives a very curious description of what this very oscillatory Hamiltonian is doing, either in a random case or in a periodic case. So what's happening is that, of course, you don't expect H or gamma n converges pointwise. However, you may play the following game. If this conjecture is true, then what is happening is this. So now I want to tell you exactly what does it mean in terms of, because I haven't defined the metric for you yet. For more excitement, I want to do it later. But I want to tell you what the consequence of the metric that is not defined would be for this conjecture if it is true. So if this it really means this. It means, so let's define some equivalent relationship between Hamiltonian functions. I say Hamiltonian function h is equivalent to k if the time 1 map of h is the time 1 map of k. Okay? You can have different Hamiltonian that at time 1, they give you the same thing. That's very possible, actually. You can easily show that you can have different Hamiltonians at time 1, they're the same. Not for all times. If for all times you have the same flow, of course the Hamiltonian must be the same, modulo a constant. But you can have a Hamiltonian that, two different Hamiltonians that they give the same flow at time 1. Then what it really means, then the conjecture means that there exists a sequence of Hamiltonian Kn such that HO gamma n is equivalent to Kn. Okay? So what's happening is that it's quite possible because of high oscillation of Hamiltonian, the energy, some of them is wasted. We don't have to use so much energy to produce the same flow at time 1. But you can switch to another Hamiltonian that produces the same flow, and then this guy has a chance to converge pointwise. It converges to the homogenized Hamiltonian. This is the one for which rescale position. Okay, this is some Hamiltonian. There exists some Hamiltonian that when you look at the time 1 map of this, coincides with the time 1 map of this. No. No. Not if it's true at one time. Okay, so there is a deep theorem of Hofer that it says that if you have a Hamiltonian function, and if you look at the periodic orbits of this, if it has no periodic orbit of period strictly less than 1 or equal to 1, then there is no way to find a Hamiltonian that will save you some energy. Otherwise, you can change the Hamiltonian locally somewhere, save the energy, increase the norm of the Hamiltonian function, but produce the same time 1 map. So, you know, it takes a while you believe these things may happen. So they kind of, to me, everything was a miracle. I mean, just I didn't know how people discovered this. But after playing with Hamiltonian ODEs a little bit, then you see that these things are all possible. Okay, now I have time to define. I want to say something about the metric. In fact, Viterbo's metric basically is equivalent to say that you have homogenization in some sense, but not for the viscosity solutions, for the geometric or variational solutions. Yes? H hat equals to H bar. H of gamma n is the same as H. You mean when it's independent of? Okay, you can add a constant. Okay, so Hamiltonian function, you mean when it's independent of position? Oh, in convex. Okay, convex case would not be included, so this should be true only locally. Convex, I think there is a problem. You see here, okay, so this should be true for Hamiltonian that is, this definitely you expect it to be true if Hamiltonian is of compact supporting momentum variable. So it does not include the convex case. The convex case, you have to modify this. I don't know how to formulate it. Yeah, that's a good point. That's right. You may assume that it's convex at infinity somehow, independent of position, and then you can concentrate on a local one. Then it has to coincide with the convex function at infinity or something. Otherwise, this would not be true. Yes, you're right. So you have to be extremely careful. For convex function, I would make a convex function that is independent of position and perturbed by a Hamiltonian function which is of compact supporting momentum variable. Then all these I can reformulate it, and all these guys can be formulated in that context. So I mentioned here that it's true for function of compact support, but I'm pretty sure you can kind of extend it to the case that is the compact support perturbation of a convex function that is independent of position. Yes. Right. Okay, so some comments about the metric. About these metrics. Okay, so there is one thing for sure, and that is no matter what metric you pick, by some soft arguments you can prove this. It turns out that if you look at any of these two metrics, or any reasonable metric you can put there, and it's not clear how many such metrics would exist, then if you look at d of so how I want to say this? Yes, if you look at d of phi h o gamma n and phi k o gamma n, then this is less than d of phi h, phi k. So if you make things more oscillatory, the distance would not increase. So you have some kind of a contraction going on. An immediate consequence of this is that if this converges for some subsequence, that the full sequence also converges. Because you see, the limit of this would be the fixed point of this operation. And since with respect to this operation, the distance cannot increase, as soon as you get close to the space of fixed points, then you cannot get away from it. You stay close, and therefore you have a unique limit. So assuming this, we can readily show that if phi h o gamma n converges to phi h hat along a subsequence, then the full sequence converges as well. Okay, again, for more excitement, I haven't told you what the metric is yet. Just want to put all the properties. So it's not hard to show that if this is true, I mean, normally you expect if let's say you look at the C1 topology on the space of Hamiltonian. If you make the Hamiltonian more oscillatory, of course, things get larger and larger, because when you differentiate Hamiltonian function, then it becomes enormous. But that is not true in this metric. You have this remarkable contraction property. Here are some properties, some more properties. Okay, so so the way to think about it is that, you see, look at the Hamiltonian function. I don't have a nice group structure that is compatible with the Hamiltonian ODE. However, if you look at the flow of a Hamiltonian ODE is the so-called symplectic. And the space of symplectic maps is a group. So you have a group structure on the space of flows. And in fact, this metric is very compatible with that group structure. So in fact, the metric, no matter what metric you pick, is in such a way that if you look at the distance between two time one map of the flow, that is given by somehow, this is the best you can think of. I mean, if you have a vector space, in order to define a metric, you first define a norm. Once you have a norm, you can turn it to a metric. Now here, you don't have a vector space, you have a group. And in fact, you define something like this, some kind of a norm of a transformation, and then you can turn this to a metric, where E, in some sense, is really D of identity and phi. So it's the best to first define the distance from identity and regard this as some kind of a norm, but it's not a norm. You know, it's the best you can do on a group. And then this is really given by the distance of this from the identity. Moreover, in fact, the space K is group, and equivalently, because of this relationship, the space of Hamiltonian function modulo that relationship is a group. So this looks like flat space, but when you look at the equivalent classes, it's not a flat space, but it turns out to be a group. One can show is a group. And all these metrics are compatible with the group structures. We have the following properties. For E. 1, E of phi is the same as E of phi inverse. 2, E of phi psi is less than E of phi plus E of psi. So it very much behaves like a norm. And the third one is that if you look at E of tau inverse phi tau, this is the same as E of phi for tau in K. And the last, not the least, that would allow me to do homogenization, E of gamma n O phi or gamma n is n times E of phi. So kind of any metric satisfies these axioms would satisfy these additional axioms that would allow me to do homogenization. Now I'm ready to finally tell you what those metrics are. So let me kind of say something about the metrics. Okay, so first Hofer metric. So I want to tell you what is the energy of phi. So this is a map that comes from Hamiltonian. So it turns out, as I mentioned before, the time one map can come from various different Hamiltonians. You minimize the amount of energy you need to construct such a map. Here, we allow, so okay, so I think maybe I should have made a comment when you ask your question. Here I allow the Hamiltonian depends on time. Otherwise, if it's independent of time, it would be much harder to do that. So you have to allow the Hamiltonian depends on time. So here we also consider H that, in other words, the ODE would be non-autonomous. That depends on time. And by H1 infinity, what I mean is this. I want to take L infinity in a space variable and L1 norm in time variable. However, the L infinity exactly is not the relevant topology for Hamiltonian function. Don't forget that if you add a constant to Hamiltonian function, it does not affect the Hamiltonian ODE, because Hamiltonian ODE involves the derivative of H. So instead of taking the L infinity, you have to allow a constant to be subtracted. So instead, I'm going to take the maximum of Hamiltonian function over x minus minimum of the Hamiltonian over x. So then I don't have to worry about adding a constant and not affecting the Hamiltonian ODE. And after that, take the L1 norm of the outcome. So that is the Hofer metric. Make sense? Okay, so now let me make a remark. And oh, I'm sorry. Here, a z. Z is x and p. Z is in x and p in the phase space. You have to take L infinity in the phase space. Yes. Okay, so let me make a remark. Okay, so in fact, it's easy to verify that this is a metric, except one axiom is highly non-trivial to show. Can you guess what that axiom is? Any guess? Or you're just too tired of it? It's actually highly non-trivial to show that if you have a flow which is not identity, then its norm is positive. Highly non-trivial. To show that if phi is not identity, then E of phi, in other words, this is a non-trivial metric, is positive. Or in other words, if you have 2 times 1 map of Hamiltonian, if they are not the same, then you can find 2 Hamiltonian functions. They produce those time 1 map, and these Hamiltonian functions are not the same, modular constant. Highly non-trivial fact. In fact, it involves many ideas from symplectic geometry, and this is related to so-called rigidity phenomenon in symplectic geometry. So it has to do rigidity. You know, all the proofs that I know are highly non-trivial. One of them uses Gromov non-squeezing thing. That is a heavy-duty complex analysis for higher dimensional manifolds. You have to solve some elliptic PDE in order to prove this. The other one involves minimax principle in when you find periodic orbits for Hamiltonian ODEs, the proof of Hofer, which is also highly non-trivial. So I know of 3 different proofs and are extremely hard to prove. This is remark 1. Remark 2. If you replace L infinity here with any other norm, LP norm, then E phi would be almost always 0. Okay, so the reason is this. See, this is a very delicate question. The Hamiltonian ODE involves the derivative of H. It seems quite possible that you construct a Hamiltonian that itself is small, but its derivative is enormous. Derivative is so large that produces a non-trivial flow for you. That seems to be plausible. But this theorem says no, not if you use L infinity norm. Yes, if you use LP norm. So if we replace L infinity with LP here, then E phi is 0 almost always. It turns out not always, but that has to do whether the integral of H is 0 or not. So I'm not going to discuss that. These are kind of like some geometric ideas. So this is a theorem of Eliashberg. And Eliashberg, I think that's how you spell it, and maybe Polterovich. In fact, there's also a theorem of Buchevsky says that any metric you choose, if you choose any norm here, and if the metric is non-trivial, that norm should be at least as strong as L infinity. So you cannot do better than L infinity. L infinity is the only possibility. Okay, so you can see how subtle the question is. Okay, so far so good? Now, let's see if I have time for more excitement. So I want to define Viterbo metric, but that involves a lot of preparation. In fact, Viterbo metric basically says that you kind of look at the Hamilton-Jacobi PDEs, and you look at certain questions, and then you minimize and maximize the energy there. So kind of in spirit is closer to Hamilton-Jacobi, but it requires a lot of preparation. It relies on some standard theory in this business, namely, first you show that the Hamiltonian solutions to Hamiltonian ODE, the solutions are critical point of some functional. You figure out what that functional is. That functional is this functional, px dot p dot x dot minus hxt t integral from 0, 1 dt. So it turns out that if you give me any curve, x and p, if you take any curve, minimized, if you look at the critical, you wouldn't minimize unless h is convex. If you look at critical point of this functional, these are solution to the Hamiltonian ODE. So there's this infinite dimensional functional for which the critical points are exactly solution to Hamiltonian ODE. Then if you have a functional, you're looking for critical points, don't try, if h is not convex, don't look for minimizer, because minimizer would not exist. You have to look at other critical points. In order to do other critical points, then there are some tricks in topology used like cohomology, algebra to find certain critical points. You know, you look at the level sets of this functional. When the topology changes, there's a critical point. So these are known as Morse theory and Lusternik-Schnirelmann theory. Then you apply that theory to this functional, but not exactly. First, you have to approximate by some finite dimensional problem, because this is infinite dimensional theory, and it's hard to do topology in infinite dimension. So you approximate by finite dimensional theory, and then you do Lusternik-Schnirelmann theory to that functional, find the critical points. Then certain critical points are exactly the Viterbo metric distance of that transformation, of that Hamiltonian ODE. Then that defines also a metric, but highly non-trivial to show that metric is non-trivial. But I think that kind of maybe goes beyond the scope of this mini course. Maybe it's a good time to stop.